To see the code running, I can press function control F5 in VS Code to run the code. This has to happen from the main file, and now that it's running, I've initialized the simulation at the correct speed of time to use the spacecraft. It's possible to zoom in and out and move around. There's a menu as well. I can show and hide spheres of influence. I draw these as purple to be different from the planets and suns so that the user does not get it confused. If I zoom in, I can see the moon, the sphere of influence of the moon, the sphere of influence of the Earth, and the spacecraft orbiting. The user is able to rotate the spacecraft as well, and then apply thrust with the space button. You can see the back of the spacecraft there turns orange to show that the engines are burning and a thrust is being produced. The velocity readout in the top corner I can also disable. Trail length can be changed with this here. That's detailed more in the testing section of the testing video. If I zoom in, I can speed up, slow down time. I can thrust to change the orbit. And if I speed up time a lot, it's possible to see that the spacecraft doesn't flip off the Earth and go flying off into space. Now I can see all the various planets moving around the Sun: Mercury, Venus, Earth, Mars. And if I zoom out even further, it's possible to see the true scale of the solar system, just the massive distances between planets. One of my favorite things is looking at the moons of Saturn and Jupiter. There's just so many. It's really nice to see them all going around. I'll demonstrate the change in trail length. It takes a while to observe, but it's possible to see how it scales in proportion to the number being shown there. Working with the trails was possibly one of the more difficult parts of programming this project. Just keeping track of all the positions. So when the point here is generated, the original position vector, the utility vector that I have in the trail point class, that finds the position basically of the point relative to the planet that it should be around. Then the method finds the position of the planet up here around the sun, way down there, and adds on basically to the position that the point should be. It adds the original position vector to the position of the planet. This also requires the use of the tree to define this relationship, so that when called, the method's able to have access to the data. Of course, gotten through a getter method, the data of the planet that the moon should be orbiting. That's about it. I will just disable the series of influence. It's possible to see without it. The velocity readout, of course, it stays still while moving this quickly, because the spacecraft is locked in place. I'm not using mechanics to move anymore. If I slow it down again, yep, it's moving again using mechanics. This decision here is justified because the user will be using this for mainly two reasons: interacting with the spacecraft and just seeing the scale of the solar system, interacting with that. At the scale that the spacecraft will be used at, time will be slowed down significantly, so that the spacecraft isn't just quickly moving around the Earth, so that the user can actually see what is going on at a reasonable pace. And at the higher scale of speed, where the spacecraft would be locked, the user is going to be much more just looking at the solar system rather than the spacecraft. Thank you for watching this. The following now will be videos of all the tests performed. Initial test. Test number 1-1A. The Q key will be held down. The spacecraft is rotating left. The Q key has been released. The spacecraft has stopped rotating. Test 1-1B. The E key will be held down. The spacecraft can be seen rotating right. Rotation ceases when the E key is no longer held. Test 1-2A. The Q key has been held down momentarily. The spacecraft can be seen pointing more leftwards than it previously was. The E key has been held down momentarily. The spacecraft can be seen pointing more rightwards than it originally was. Test 1-3A. The spacecraft has been initialized between Earth and Venus with no initial velocity. It moves down towards the Sun in an unexpected spiral wavy pattern. Test 1-3B. The spacecraft has been given an initial starting velocity of 20,000. It noticeably moves more to the right before resuming its spiral pattern down towards the Sun. All the time, a trail is being drawn out behind it. Test 1-4A. This test is currently not possible as the spacecraft is not able to achieve stable orbit. Test 1-4B. This test is currently not possible as bugs prevent the spacecraft from achieving stable orbit. Test 1-5A. This test is not currently possible as bugs prevent the spacecraft from achieving stable orbit. Test 1-5B. This test is not currently possible as bugs prevent the spacecraft from achieving stable orbit. Test 1-6A. The very first loop shows Earth printed to the terminal. Test 1, 6B. The first loop shows that the spacecraft is inside the sphere of influence of the Moon. Test 2, 1A. Planets can be seen forming a dense white trail of points behind where they move around the Sun. Test 2, 2A. No series of dense white points can be seen forming behind the Moon as it moves around the Earth. Test 2, 3A. When zoomed out, a series of 8 white trails around the Sun can be seen. Test 2, 4A. When zoomed into the Earth, the sphere of influence of the Moon can be seen, however there is no arc of the trail of the Moon present. Test 2, 4B. When zooming into Mars, no indication of any moons can be seen. Test 2, 4C. When zooming into Jupiter, no other indication of moons can be seen. Test 2, 4D. When zooming into Saturn, no other indication of any moons can be seen. Test 2, 7-1A. Data for the spheres of influences of planets is reasonably accurate to their known values. Test 272A. Values for the sphere of influences of moons in the solar system modeled are accurate enough for the requirements of the program to those in real life. Test 28A. When zooming into the Sun, it is seen as a yellow circle. Test 28B. When zooming into a planet, it is seen as a white circle. Test 3-2A. The value calculated by the program is the same as the actual value. Test 3-3A. Values calculated by the program match up to actual values. Test 3-4A. The force calculated by the program matches the actual value. Test 3-6A. The first calculated velocity in the y-axis is accurate enough to the actual value. Test 4-7A. The values calculated by the program match up to the accurate values. Test 4-7B. The orbit of Mercury has been timed. It has taken 2 minutes and 10 seconds. Test 481A. The value calculated by the program matches up with the actual value. Test 481B. It has taken the moon 27 seconds to orbit the Earth. This matches up with the value specified in the program. Test 482A. All calculated positional values match up. Test 482B. When looking at the Earth as it moves along in its orbit, it is possible to see that the moon stays within the sphere of influence of the Earth. However, all other moons, apart from the moon of the Earth, are not in their correct positions around the planet that they are orbiting. However, they are around the Sun instead. Test 51A. The left arrow key has been pressed. Everything on the screen appears to move to the right. Test 51B. The right arrow key has been pressed. Everything appears to move to the left. Test 51C. The up arrow key has been pressed. Everything appears to move down. Test 51D. The down arrow key has been pressed. Everything appears to move up. Test 52A. A downward scrolling motion has been done. Everything on the screen appears to grow in size, except the sprite of the spacecraft, which stays in the same position. The focal point of the zoom seems to be the top left corner. Test 53A. An upward scrolling motion has been done. Everything has appeared to shrink in size. The focal point seems to be the top left corner. The sprite of the spacecraft has not changed in size, and also has not changed its position. Test 54A. The right bracket key has been pressed. Planets speed up, the spacecraft slows down. It has been pressed again, planets have sped up even more, and the spacecraft has slowed down even more. Test 55A. The left bracket key has been pressed. The spacecraft has sped up, and the planets have slowed down. The more that it is pressed, the more the planets slow down, and the more the spacecraft speeds up. Test 56A. The backspace key has been pressed. The motion of the spacecraft has stopped. The motion of the planets has also stopped. The user is still able to use the arrow keys to move around, and able to zoom in and out. Pressing the backspace key again stops the pause effect, and motion is restarted. Test 57A. The user's region of view has been moved far outside of the solar system. By pressing Tab, we are able to reset to the original view, with the focal point being in the top left rather than in the middle. Test 58A. The button to open the menu shall be clicked. The menu has opened on the left side of the screen, displaying all the buttons and selectors inside of it. Test 58B. When the button to close the menu is clicked, the menu is closed. The user is able to close and open the menu. Test 581A. When the button is clicked to show the force vector, it can be seen protruding from the spacecraft sprite, which does not match the location of the actual spacecraft. The direction of the vector seems offset at an angle to what it should actually be. When selected to not show the force vector, the blue line disappears and is not drawn onto the screen anymore. Test 582A. When selecting to show the velocity of the spacecraft in vector form, a pink line is drawn from the position of the ship's sprite. This position is, however, not the actual position of the spacecraft, and the direction of the pink line matches the direction of motion of the spacecraft. When the setting is turned off, it is no longer drawn onto the screen, and the pink line disappears. Test 583A. The spacecraft has been given a starting velocity of 50,000. The initial starting velocity matches the one that has been drawn on the screen at the start of the program. When turned off, the readout disappears. When turned on, it reappears. Test 584A. We can see here that both the spheres of influence of the Moon and the Earth are shown. When turned off, they disappear. When turned on, they reappear again, drawn as purple circles. Test 585A. When pressing the top button, the percentage indicator increases. Then, looking at the trail lengths of planets, taking for example as Mercury, we will be able to observe a change in the length of trail. The length of the trail around the orbit that is left has now changed to be shorter, taking up roughly 20% of the circumference of the entire orbit. When looking at the spacecraft, if the trail length is increased, and if we wait a while, it is observed that there is no change to the length of the trail of the spacecraft. Test 585B. When the bottom button is pressed, the percentage shown decreases. If we wait a while, we are able to see that there is no change in the length of the trail of the spacecraft. We are able to observe a change in the length of the trail of the planets, opposite to the indicated change in trail length. The region in which there is no trail shown is roughly proportional to 20% of the circumference of the orbit. Test 586A. The quit button in the menu will be pressed. The program has closed. Test 586B. The escape key shall be pressed. The program has closed. Follow-up test run. Test 13A. The spacecraft moves down towards the sun. There is a straight line of dense white points formed behind it as it moves. Test 13B. The spacecraft has been initialized with a little velocity in the x-axis. It is possible to see parabolic motion and a parabolic line of dense white points down towards the sun. Test 14A. The spacecraft is going to do a prograde thrust to raise its orbit. The space key has been pressed to apply a thrust. There was a brief visible orange spot at the back of the spacecraft showing that the engines are burning and thrust is being produced. The spacecraft's position has raised significantly from its last orbit. Test 14B. The spacecraft has been initialized in an orbit of the sun. A retrograde thrust is going to be applied to lower the orbit of the spacecraft. The space key was pressed for a short amount of time to apply a retrograde thrust. It reaches a lower position than its previous orbit. Test 15A. The spacecraft has been initialized in an orbit around the Earth. We can see that the trail of the spacecraft is moving along with the Earth as the Earth goes around the Sun. Test 15B. The spacecraft has been initialized in an orbit around the Moon. It is possible to see that the spacecraft is moving around the Moon, and that the trail which is following the motion of the spacecraft is relative to the Moon, and is moving alongside it as well. Test 22A. When zooming into the Earth, it is possible to see a sphere of influence, trail, and another body that is the Moon. 24A. When zooming into the Earth, another sphere of influence and trail can be seen. Test 24B. When zooming into Mars, two trails can be seen. The moons of Mars are very small, so it is only possible to see the spheres of influence and bodies of these when zooming in very far. However, they do still leave trails. Two, 4C. When zooming into Jupiter, it is possible to see four trail arcs and the spheres of influences of these moons. 24D. When zooming into Saturn, it is possible to see 6 trail arcs around it. When zooming in further, it is also possible to see the spheres of influence of all these moons. Test 4, 7b. It took Mercury 88 seconds to orbit around the Sun. The slowdown effect has been reduced, and this is accurate to the amount of time it would take Mercury to orbit around the Sun in days. 482b. The Moon stays within the sphere of influence of the Earth and moves alongside the Earth as the Earth goes around its orbit of the Sun. As previously observed, all the other moons do this as well. Test 5.2a. A downward scrolling motion has been done. Everything on screen appears to grow larger as it zooms in. The spacecraft's size remains constant, however, its position is still offset as we zoom in. Test 5.3a. An upward scrolling motion will be done. Everything on the screen appears to grow smaller as it zooms out. The size of the sprite of the spacecraft remains constant, however, is still offset by the zooming motion. The focal point seems to be in the center of the screen. Test 5.4a. First, I will observe the changes in velocity of the spacecraft. The right bracket key has been pressed. Both the spacecraft and the Earth have sped up a little bit. The right bracket key has been pressed again. Both are now moving faster. It's been pressed again, and the increase in speed is noticeable. Now I will zoom out and observe the increase in speed to planets around the Sun. The right bracket key has been pressed a number of times. Planets are now moving a lot faster than before, and if the right bracket key is pressed again, another noticeable increase in speed is visible. Test 5.5a. First, I will observe the spacecraft. I'm going to speed it up a little bit so that I can observe the slowdown. The right bracket key has been pressed a little bit, and now it's time to observe the slowdown effect. The left bracket key has been pressed, both the spacecraft and the Earth are moving slower. The left bracket key has been pressed again, both are moving a lot more slower than last time. Now I'm going to zoom out and view this effect on the planets. First, I will increase the speed to be able to observe the slowdown effect by pressing the right bracket key a couple times. Planets are now moving quite fast. The left bracket key will be pressed. Planets have slowed down. The left bracket key was pressed again, and they've slowed down even more. Now I will observe the effect on moons. Zooming into Jupiter. The left bracket key has been pressed, moons have slowed down, again, and they slow down even more. Test 5.7a. The region of view is going to be moved outside of the solar system. Now the tab key shall be pressed. The region of view has been brought back to the center of the solar system, the Sun. 5.8.1a. The toggle to show the vector of force will be turned on. A thin blue line can be seen protruding from the spaceship, showing the direction of the force. The force on the spaceship is showing towards the center of the Earth due to this being the predominant gravitational influence on the spacecraft. When turned off again, the thin blue line disappears. 5.8.2a. The option to show the velocity vector will be turned on. A pink line can be seen protruding from the spacecraft, forward and slightly downwards. When turned off, no more pink line is observed. 5.8.5a. First, I'm going to check the trail length of the spacecraft. I'm going to press the top button to increase trail length. The percentage number increases. After waiting a moment, it is possible to see that the length of the trail of the spacecraft has also increased. Now, investigating the trails of the planets. Currently, the trail takes up around 50% of the orbit of the planet. When I press the top button, it increases the number, percentage, and after waiting a while, it is possible to see now that the trail is longer and takes up about 80% of the circumference of the planet's orbit. Now, looking at moons as well, it's possible to see that the trails of moons also take up around 80% of the circumference of their orbit. 585b. First, looking at the trail of the spacecraft, when pressing the bottom button, the percentage indicator decreases. Looking at the length of the trail of the spacecraft, it has decreased and become shorter. Now, looking at the orbits of the planets, when I press the bottom button, the percentage indicator decreases, and after waiting a while, it should be visible that now the trail of the spacecraft has shortened. The area that it takes up of the orbit of the planet is proportional to the percentage indicated. Looking as well at moons, the area of their orbits that the trail is in is also proportional to the value indicated. Hello, this is a short tour of my code that I've written. This is the main.py file. This is where the simulation class has been put. Each class has been split into a separate .py file to increase readability and make it easier to view aspects of code. The simulation function has a very long initialization. Here, all the menu and front-end bits are initialized. There's also the solar system tree structure that requires initialization. This uses classes from other files that are imported at the top. Then here's the main function. This basically ties everything together. This here is represented in a flowchart in the design section. There's a couple getter methods. These are used by the camera class. There's the input check. This checks for inputs from the user, from the keyboard, and with clicks and everything. Here are my 3 tree traversals. The creation traversal here at the start is only used during initialization. This creates the spheres of influence, the radius for each of the planets and moons in the solar system. Then I have the position update traversal. This updates the positions and trails of every planet and moon. And then this here locates and tells the program which planet or moon's sphere of influence the spacecraft is in. This is used for keeping the trail of the spacecraft relative. Then the last one here is the draw function. This is responsible for tying together all the other draw self functions and also drawing the menu and all the buttons there. Next, I'll go to the camera file. Here to the left are also the assets. There's sprites for the menu and the spacecraft, as well as a font imported for text. The camera file here has a much shorter initialization. There's just 2 vectors here in use. The position, the original position vector, which would just be the center of the screen scaled, and the actual position of the camera, and you can move this around to change the region of view. It can also follow the ship or not. If it follows the ship, then it would make use of this function, which just tells it to have the same center of the screen as the position of the ship. So you would have the ship in the center of the screen always while following the ship. Then there's this quite long function. This takes the simulation and grabs all the main aspects from it, the solar system, the ship, and it also needs the zoom because that's taken into account. This just creates scaled positions for each of the planets, moons, the sun as well, and for the ship. So this is used to update, or basically take from the accurate positions, it takes a scaled value and creates a new set of positions. Then next, I'll go to simulation objects. This is just an abstract class used to start the class hierarchy. Putting this in its own class simplifies things a lot and reduces repeated code. It's got the 2 vector positions, the actual position and of course the scale position that the camera creates. And then it's also got methods to set these to a different value. Next, I will look at stars. This is just on the class hierarchy. Stars are static. It's just the sun. They don't need methods to move or anything. They just got getter methods drawing themselves. It's just a pygame draw circle function. And yep. Of course, then with inheritance, I'm able to add on to that with the planet class. It's got slightly longer, more attributes are necessary for motion. It has an angle around the sun. For example, at the start of the program, the angle is 0. It is directly in a horizontal line with the sun. But as it orbits, and that's dependent on the period, the time it takes to complete one orbit, the angle will change. It's got better methods as well to protect the integrity of its attributes. Update position, of course, just using some trigonometry. It also has an update trail and the create sphere of influence function. This is inherited by the moon. A lot of these are. Some are polymorphic. For example, draw self appeared previously with the sun as well. This one's slightly more complicated. It also needs to draw the sphere of influence and the trail. But apart from that, the final class in this hierarchy is the moon. It's just got specialized functions since it inherits most of them. It has a follow planet because it also needs to stay around the planet. This just takes the position of the planet and adds the position of the moon onto that. So normally, if this wasn't there, the moon would be orbiting around the sun actually. But what is then done is that the center point, which would be the sun, without this, it just takes the planet as the center point. So it finds the position of the planet and puts the moon around that rather than the sun. Then of course, update trail is also a bit more complicated because the trail needs to be relative to the planet. So it needs to do roughly the same thing there. For some moons, their orbit is so short that it's hard to have enough points for the trail. In this case, the trail just creates points all the time. In other cases, trails have a little timer so that they don't create too many points to decrease performance. That was that hierarchy. The spacecraft here, that is also a child class of the simulation object. Most things on screen are child classes of the simulation object. It's got some other values here pertaining to the motion. It has a slightly different concept for motion. It uses, over here in update position, it uses Suvat and some mechanics formulas to have a dynamic motion. So it's not just going in a circle, it can also be changed by the user. There was a slight problem. I've mentioned this in the conclusions to testing. If the time in between each moment where we'll be calculating this is too great, then there's an inaccuracy with the position, and the spacecraft gains energy out of nowhere. At lower speeds of time, this isn't a problem. That's why I've got this here, so that when the time is sped up, the spacecraft is basically frozen in place around whatever it was orbiting, whether that be the Earth or the Moon. Not around the Sun, though, because around the Sun, it wouldn't really have the slower speeds. It would be moving faster, and you'd have to have faster time as well. If you go too fast, if you increase the time passes in the simulation, then without this, the spacecraft would be flung off course from the planet. With this, it's possible to look at the spacecraft orbiting the planet, then speed up time, look at planets orbiting the sun, and then slow time down again and return to looking at the spacecraft. Without that, if you were to speed up time, the spacecraft would be flung off and you'd lose your stable orbit. Apart from that, there's also another small trigonometric function here to apply thrust. Because of the two-dimensional coordinate plane, a lot of resolving forces is necessary, which uses trigonometry. This here is also another A-level physics formula. This is used to calculate gravity. It does this for each body in the solar system, the sun, all the planets, all the moons, and then it finds this, gets it into the vector that the spacecraft has for force, and just by adding all of these to the same thing, finds the resultant. Apart from that, it's also got update trail, which is additionally probably the longest update trail function, or method. This needs to take into account that the trail should be relative to planets and moons as well. So it has to do roughly the same thing that the moons are doing, taking the position of the planet or the moon in this case, and adding on to the trail for that. This is explained in more detail in implementation and with comments. Draw self, there's the additional bit here of drawing the vectors for both velocity and force. It needs to find position tuples to draw these vectors from. They're just drawn as a pygame line. Then after the ship, the final object in the hierarchy of the simulation objects is the trail point. These are used by all the other classes that I've just mentioned to basically draw a trail behind them. The trail point is also just drawn as a pygame line, but it's so short that it appears just as a point on the screen. It's not super complicated. It has this additional vector. This is used differently by different classes, but basically, for example, the moon will use it to find the difference in position between the point and the planet, so that it can add base the position of the trail around the position of the moon plus this additional vector. It then also has a function to change this value, and no, a method. And it's also got another method to change the color gradually as it fades out. So it has a timer that determines the amount of time it should be alive or on the screen for. And as this timer runs out, it gradually grays and gets darker to give a bit of a gradient fading out. Then, apart from those classes, there is also the vector class. It's just used to store an x and a y and protect those attributes. There's also two other abstract data types. The queues class, 2 pointers, and the queue. It's used in tree traversals. And the stacks class, also used in tree traversals. The width first or breadth first traversals use the queue. The depth first traversals use a stack. That's about all the code that I've written. Libraries that I'm using: OS, Pygame, and in some of them the math library. I'm sure, yep. Math library, OS, and Pygame libraries are used.